Okay, guys, it's nice to see you guys. And actually, I presented this poster via ICDM Workshop. I submitted this paper at June in my memory, if it's correct. And I presented this on maybe September or October, I think. But actually, it's been a while, but I wanted to record this because at that time, it was my first time presenting in front of many people, like some top tier conferences. And now I wanted to leave this presentation as my private asset too. That's why I'm recording this video. And let me start my presentation here. Um, to introduce myself again, I'm John Park, and the title and topic I'm presenting is MAMBA-PAD, the selective state-space anomaly detection with channel-wise gating and stabilized dual objective training. This work was done at the Department of Applied Artificial Intelligence and Samjeongan University in South Korea, and my advisor is Hayang Oh. Okay, so let's begin. So, why is existing anomaly detection not enough? Well, time series anomaly detection plays a crucial role in safety critical domains such as healthcare, aerospace, and IoT, and so on. We need models that can detect abnormal behaviors both accurately and quickly. However, existing approaches each have clear limitations, and those are the bullets that I wrote. Classical detectors models like iForest, LOF, or RRCF are efficient, that's right, but cannot capture temporal dynamics. Transformers or GAN-based models are quite accurate, but computationally expensive and unstable in deployment. And thirdly, the graph-based methods require prior relational knowledge, so they don't generalize across domains. That means we need a model that is accurate, interpretable, and deployable. So that that can lead us to some research questions. First, can one model detect both burst type and drift type anomalies simultaneously? Second, can multivariate anomaly detection become interpretable without graph priors? And lastly, can training remain stable and efficient under class imbalance or strong periodicity? So these are the questions. And to answer these research questions, in my paper, I proposed the MAMBA-PAD, and the third section is about MAMBA-PAD's model architecture and the methods. So MAMBA-PAD, a selective state-space framework that achieves adaptive delta T gating to unify burst and drift detection, and second, channel-wise gating for variable level interpretability, and dual objective training with alpha annealing and threshold calibration for robust stability. So I'll show you. I don't know if this image is shown like, clearly, but anyway. Would you look at figure one, which is this part under how does MAMBA-PAD work? Yeah. At the top, the model receives normalized multivariate inputs. They are embedded in two ways, temporal embeddings encoding position and time of day, and feature embeddings capturing rolling statistics and lightweight projections. These embeddings are segmented into multi-scale windows, which are fine, medium, and coarse, so that the model can recognize both sudden spikes and gradual drifts. Then comes the innovation, in my opinion, actually, adaptive, adaptive delta gating. A small MLP predicts the step size delta t at each window, and large delta t values make the model react faster and focus on burst anomalies, while small delta t keeps longer memory to capture drifts. In this way, the model automatically adjusts its temporal resolution That's how we unify both anomaly regimes. Next, channel-wise gating computes a separate sigmoid gate for each variable. Oh, sorry, the screen wasn't going down. Anyway, where should we begin? Yeah. Well, I'll show you the channel-wise gating computes a separate sigmoid gate, and it activates only the channels that are relevant to current anomaly. This enables interpretable multivariate detection without any graph prior, to be clear. Finally, the outputs go through two heads, and one is for reconstruction and one is for classification. The loss is defined as here, and alpha gradually decreases 0.7 to 0.2 during training. Yep. And we also apply validation calibrated thresholds to control false positive and a periodicity aware fastpass to speed up the convergence on cyclic data. Actually, the resource was quite an important issue to us during experiments. So, does MAMBA-PAD really work? Yeah, moving to the results on the right, we evaluated this MAMBA-PAD on 8 public benchmarks, including NAB, SMAP, MSL, NIC taxi, ECG anomaly, machine temperature, network traffic, and CPU utilization. Across these datasets, our model achieved an average F1 score of 0.86, plus minus like 0.07, and an AUC of 0.93, with only 14 milliseconds of inference latency and less than 1 minute of total training per dataset. It outperformed the best baseline on the 6 of the 8 datasets. The improvements mainly comes from adaptive totality handling, slow drift in NASA telemetry, and channel-wise gating highlighting the correct sensors in ECG and temperature data. If the dataset is strongly periodic, like CPU utilization, let me show you more clearly here. Yep. Well, we still see challenges, but our calibration and fastpath reduce false alarms substantially, and the result clearly shows it. So let's move on to the next conclusion part. To summarize, MAMBA-PAD extends selective state-space models to anomaly detection by introducing adaptive delta gating and provides channel-wise interpretability and stabilized dual objective training for robustness, and also achieved high accuracy real-time speed and clear variable-level insights across multiple domains. In the future, we plan to explore more label-efficient online adaptations and integrate MAMBA-PAD with diffusion or cross-attention mechanisms for more dynamic temporal reasoning. Well, that's today's conclusion, and it was really to share my presentation again. Thank you for listening, and I'll finish my recording.